Hello, I'm Andrew and I'm a field application engineer with Omron. During this video, I hope to give a practical introduction to using cam synchronization with any Omron NX or NJ controller. So, what do we mean by the word cam? Well, like a mechanical cam, a cam inside the motion control refers to a relationship between one axis and another, a fixed positional relationship. In these videos, we can see such a method being used inside motion controllers to produce cam controlled motion. It's a flying shear we have, and next is a rotary knife operation using cam synchronization. So, by way of understanding how we implement cam solution, let's define a mechanical solution to a problem. So the problem we have is a box upon which we wish to deposit a green line of something, and the box travels along a conveyor, and the green line needs to be perpendicular to the travel of the box. So we can define a mechanical arrangement to provide the solution and to be able to build our software program and configuration. As you can see on the sketch, we have a y-axis actuator which will take the green pen across the box. This process is probably going to be time dependent because of the way the ink flows. Similarly, a cutter would also be time dependent based on the cutting speeds needed. And because it's time dependent, we won't be dealing with that in this solution. What we will deal with is the travel in the x-axis in the direction of the master axis or the conveyor. The belt sensor is there, and I shall deal with that in another session to locate the product and position the x-axis where we wish to in the travel on the box. Here we can see a velocity profile. There are two axes on the left, the x-axis speed and the conveyor speed. And you can see that for 500 millimeters of travel, they need to match to create the perpendicular line. We also have defined an acceleration distance and deceleration distance, the total of which is 600 millimeters in one direction of the x-axis, this in the direction of the conveyor. So, to return the x-axis carriage to its beginning position, we must move backwards in the return phase 600 millimeters. That defines our x-axis motion. On this slide, I'm trying to illustrate how, using simple schoolboy geometry and motion equations, we can quickly build the important figures which we will need to create a table of points to define the positional relationship between the master conveyor axis and the x-axis slave. So finally, we're able to derive, using those numbers, a lookup table for master and slave, and we use the Sysmac software tool to input those values and create a CAM profile. Okay, so now we want to create the solution on the NJ using Sysmac Studio. So we'll go for a new project, give the project a name. We're going to select an NJ controller. Almost all of the NJ and NX controllers have CAM functionality, only the very small ones don't. So I'll just arrange my windows and begin configuring the axes. So we'll need 2 motion axes. I'm going to call one my virtual master, which represents the conveyor. I'm going to add another axis called the slave, which represents the carriage that runs with the conveyor. I want to use millimeters as units, and this is where we relate the encoder pulses to the travel distance for our particular mechanics. We need to take care of some of the limits, and for this axis on the conveyor we're going to have a modulo value of 5,000, which is 5 meters. This is just to set the rollover point as the conveyor travels in one direction forever. So here we're selecting rotary mode and 5,000. Similarly, for the slave axis, we're selecting millimeters. We're scaling the encoders to the distance traveled for that particular mechanical arrangement, taking care of some limits. And here we have linear mode selected already, so I'm happy with that, and we can leave that as it is. So we have now finished setting up the axes, and we're going to open up the CAM profile with a right click and create a CAM table definition as we did on the paper work we did already. Again, I like to give something a name. Now we have to complete the settings for the CAM table. I'm going to work with millimeters. I'm going to start to add CAM points as we'd already defined. Okay, so if I can't add any more, it's because the face pitch is too small, which means we haven't got enough points. So adjusting that bigger allows me to continue entering the CAM that we've defined. Now if I look at the velocity and acceleration profiles that for the CAM that's been defined, I can see that the acceleration has spikes and the velocity has steps. So we'll look into that and we'll correct that. It's because of the type of curve we've selected. So we select polynomic 5 to give us a smooth motion. And then we can readjust the axes scales by clicking, and with a wheel on the mouse you can adjust those axes at the side. So I'm happy with the configurations. Now we have to create a program. Just renaming using the right click. As you can see, I'm adding one program for the conveyor, one program for the slave, one section rather for the slave. So for the conveyor, we just need to run the conveyor. So I'm going to use one instruction called MC move jog. Because the axis is a virtual axis, I do not have to use the MC power function block, which I normally would. Also, I'm not going to be running in the negative direction, so I don't need to fill that one in. I give my velocity a name and my acceleration a name. And Sysmac Studio automatically assigns the correct data types. And in the variable section, I'm able to enter an initial value. So I choose some initial values and I just comment these with an optional comment. And now we create a section of code to handle the slave. We use the MC cam in function block. That's the MC for motion control. So I'm defining the master axis and the slave by entering those names, entering the name of the cam table that we've defined. And then we have a selection of variables that we need to feed into the cam in function block to describe how to synchronize. The synchronization I want to achieve is to define a start position of the master. So for us, that can be any value between 0 and 5,000 millimeters. So any conveyor position, I just want to be able to say, okay, when you see that position, begin your synchronization. So the photo sensor could detect the box or the product, and then from that detection, we define the start position and use the start sync execute function block after defining the start position to carry out the task. Instead of initializing the variables, I'm going to use a section of structured text code in the program, and I used the system boolean p first run just so I can gain some visibility on what values I'm using on that function block within the program. I'm going to select the periodic input to be false, so that means the cam will execute once and not repeat itself. So there's quite a few variables to enter. Okay, I can see that there's some red still showing, so I have a couple of mistakes. So I've made a mistake on some of the variable entrances there. Okay, I still have an error. Okay, so I've repeated a name, so I'll just check those. Looks okay now. Just build, no errors, okay. I'm going to run the simulation. Okay, looks like I already have a simulation running somewhere else, so I'll just close that down. Try again. Okay, now the simulation's running. I'll just need to check on some variables, so I'm going to use the watch window for that. Okay, now we can run, and we can see that the virtual axis is running, so that's the conveyor running. And now I want to define my start position where I want the cam to execute. I'm defining it 155 millimeters. And in order to track the profile, I'm going to use the data trace. Just going to adjust my window and enter the values I want the data trace to record. So that's the virtual master position, slave position, and the slave speed. And I'm going to trigger the trace with some pre-trigger as soon as the slave starts to move above 2 millimeters per second. So we'll start the trace, and now we'll be waiting for the trigger. Okay, so now we can start the synchronization, and we can see the move profile has been executed. I'm just adjusting the axes using the wheel on the mouse. Everything looks okay. So I hope you found that introduction to cam synchronization useful, and thanks for watching. Bye.